Welcome to this tutorial on solving second-order non-homogeneous differential equations using the method of undetermined coefficients. This is a powerful technique that helps us find particular solutions to differential equations with specific types of forcing functions. Let's start by understanding the standard form of a second-order linear non-homogeneous differential equation with constant coefficients. The equation is written as y double prime plus a times y prime plus b times y equals g of x, where a and b are constants, and g of x is called the non-homogeneous term or the forcing function. This g of x is what makes the equation non-homogeneous. If g of x were 0, we would have a homogeneous equation. The general solution to this equation has a specific structure. The complete solution, y of x equals y sub h of x plus y sub p of x. Here, y sub h is the general solution to the homogeneous equation, which is when g of x equals 0. And y sub p is a particular solution to the full non-homogeneous equation. Our task will be to find both of these components to construct the complete solution. Let's first focus on finding the homogeneous solution, y sub h. We start by writing down the characteristic equation, which is our squared plus a times our plus b equals 0. This comes from substituting y equals e to the power of our x into the homogeneous equation. After solving this characteristic equation, we have three possible cases for the roots. Case 1, if we have distinct real roots r1 and r2, then the homogeneous solution is y sub h equals c1 times e to the power of our 1x plus c2 times e to the power of our 2x. Case 2, if we have a repeated root r, then the homogeneous solution is y sub h equals the quantity c1 plus c2 times x, all multiplied by e to the power of our x. Case 3, if we have complex roots alpha plus or minus I times beta, then the homogeneous solution is y sub h equals e to the power of alpha x times the quantity c1 times cosine of beta x plus c2 times sine of beta x. Here, c1 and c2 are arbitrary constants that we determine from initial conditions. Now let's focus on finding the particular solution, y sub p, using the method of undetermined coefficients. The key idea is to make an educated guess for the form of the particular solution based on the form of g of x, and then determine the coefficients. Here's a table of common forms of g of x, and the corresponding trial forms for y sub p. If g of x is a polynomial of degree, and then we try a general polynomial of the same degree. If g of x is an exponential function, we try a constant times that same exponential. If g of x involves sine or cosine functions, we try a linear combination of sine and cosine with the same frequency. For products, like a polynomial multiplied by an exponential, we multiply the corresponding trial forms. But there's an important consideration. If our trial form for y sub p contains terms that already appear in the homogeneous solution, y sub h, we need to modify our guess. The rule is, if the trial form overlaps with y sub h, multiply by x enough times until the result is linearly independent from y sub h. For example, if g of x equals e to the power of lambda x, and e to the power of lambda x is already in y sub h, then we use y sub p equals a times x times e to the power of lambda x. If this is also in y sub h, which happens when lambda is a repeated root, we multiply by x one more time, giving y sub p equals a times x squared times e to the power of lambda x. Once we have the correct form for our particular solution, we need to determine the coefficients. Step 1. Substitute our trial y sub p into the original differential equation. Step 2. Compute the derivatives y prime sub p and y double prime sub p. Step 3. Plug these into the left side of the original equation. Step 4. Equate coefficients of like terms with the right side g of x. Step 5. Solve the resulting algebraic system for the undetermined coefficients. Let's illustrate this with an example. Let's work through a complete example to demonstrate the method of undetermined coefficients. Consider the differential equation, y double prime minus 3, y prime plus 2, y equals e to the power of x. First, let's find the homogeneous solution. The characteristic equation is our squared minus 3, our plus 2 equals 0, which can be factored as the quantity r minus 1 times the quantity r minus 2 equals 0. So our roots are our equals 1 and our equals 2. Since we have distinct real roots, the homogeneous solution is y sub h equals c1 times e to the power of x plus c2 times e to the power of 2x. Now, let's find the particular solution. Since g of x equals e to the power of x, our first instinct might be to try y sub p equals a times e to the power of x. However, we notice that e to the power of x is already part of our homogeneous solution, so we need to multiply by x to ensure linear independence. Our adjusted guess is y sub p equals a times x times e to the power of x. Now let's compute the derivatives. The first derivative is y prime sub p equals a times e to the power of x times the quantity x plus 1. The second derivative is y double prime sub p equals a times e to the power of x times the quantity x plus 2. Now, let's substitute these expressions into our original differential equation. Y double prime minus 3, y prime plus 2, y equals e to the power of x. The left side becomes a times e to the power of x times the quantity x plus 2 minus 3 times a times e to the power of x times the quantity x plus 1 plus 2 times a times x times e to the power of x. Factoring out a times e to the power of x, we get a times e to the power of x times the quantity x plus 2 minus 3x minus 3 plus 2x. Simplifying the expression inside the parentheses, a times e to the power of x times the quantity negative 1. Since this must equal our right side, e to the power of x, we have a times negative 1 times e to the power of x equals 1 times e to the power of x. Therefore, a equals negative 1. So, our particular solution is y sub p equals negative x times e to the power of x. Finally, the complete general solution to our differential equation is the sum of the homogeneous and particular solutions, y equals y sub h plus y sub p, which is c1 times e to the power of x plus c2 times e to the power of 2x minus x times e to the power of x. This is our complete solution to the original non-homogeneous differential equation. The constants c1 and c2 would be determined from initial conditions if they were provided. Let's summarize the steps for solving second-order, non-homogeneous differential equations using the method of undetermined coefficients. Step 1. Find the homogeneous solution y sub h by solving the characteristic equation. Step 2. Choose an appropriate form for the particular solution y sub p based on g of x. Step 3. If necessary, multiply by x to avoid overlap with the homogeneous solution. Step 4. Substitute your trial solution into the original equation and determine the coefficients. Step 5. Combine the homogeneous and particular solutions to get the general solution. With practice, this method becomes a powerful tool for solving a wide range of differential equations that commonly appear in physics, engineering, and other applications. Thank you for watching.